afternoon, everybody. My name's Rick Leva. I'm with Balin Corporation, and we are the exclusive supplier for the Baxter Robot from Rethink Robotics here in Northern California. And we're a supplier of automation and process control solutions all over the western United States. So Rethink Robotics was started in 2008 by Rodney Brooks, and some of you might be familiar with his name. He's the founder of iRobot. You probably have a Roomba at your house. Goes around vacuuming and cleaning everything. He developed that robot. He was also the manager for the artificial intelligence in the robotics lab at MIT for 10 years. Very influential in the robotics industry. So he developed the Roomba and found that he couldn't build it in the United States. All right, so he wound up taking it over to China eventually and having it built there. And then found that some of his intellectual property was stolen, right, and that all of a sudden had all these knockoffs. So he really struck a chord with him on how can we get manufacturing back here in the U.S. So he did a symposium for Google called Solve for X. I don't know if any of you are familiar with that, right, but it's where they get some of the top brains in the U.S. to solve problems, right, and give presentations on this. So Rodney did one on bringing manufacturing back to the United States. So we're going to watch a couple minutes video on this.
I'm going to talk about American manufacturing, how we solve for American manufacturing. American manufacturing is not dead, despite many people thinking that. It's a $2 trillion enterprise. Chinese manufacturing is $2 trillion, European manufacturing is $2 trillion, Japanese manufacturing is $1 trillion. So that just gives you a size of the scale of manufacturing. But American manufacturing has, I think, lost its ways in many ways. It hasn't had the information technology revolution that everything else in our lives has had. And we have we've made it less resilient. After Fukushima in 2011, 10 days later, American manufacturers started shutting down because the supply chain went via Japan and things were not resilient. So how do we make it resilient? We have made American manufacturing efficient by outsourcing the low end. We started after the Second World War by going to Japan, where it was a technological society, economy was in ruins, low-cost labor. But as the economy came back up, it was no longer low-cost labor. So we moved. We headed off to Korea, low-cost labor. The society grew, people became more aware, people moved up the value chain, and it became too expensive. We moved to Taiwan. Same thing happened there. Manufacturing was cheap there originally, but it became more expensive. So then we moved into southern China via Hong Kong. The same sort of thing happened. By the early 90s, it was too expensive to do sewing for toys in China, by the late 90s. And so we started moving down to Vietnam in the late 90s. And there things go up. And eventually we run out of places to go do low-cost manufacturing. But doing low-cost manufacturing in the far distant places has had a bad impact on our innovation, because the innovation tends to move to those places. The innovation doesn't happen back here where the innovators are. So there's some movement happening out there in the world now. There's a bunch of people doing different things, coming together in small groups, and they're spread out across the country, not just in Silicon Valley, not just in Boston. There's stuff happening where there's makers, there's tech shop, there's all this sort of bottom-up stuff. How do we build stuff ourselves? How do we make that happen? And I think that's the core of a great idea. So there are people out there making stuff. Some of you might know Chris Anderson up in the right-hand corner. He just left Wired to go to his maker space where he's building stuff for do-it-yourself drones. But there's lots of people. Bottom right there is a MakerBot, which is a 3D printer. You see it's made out of wood. Out of New York City. There's a lot of people doing this stuff. They're just bubbling away at stuff. And it reminds me a lot of something that most of you are too young to remember, but I remember Silicon Valley in around the late 70s, the Homebrew Computer Club led to us here. That led to what we all have. It led to people trying out ideas, then venture capitalists coming in, a whole infrastructure coming in on top of that, and we got to where we are today with information technology. So that's starting to happen with manufacturing and doing it yourself, building stuff yourself. But it needs a bunch of things. The computer revolution, the IT revolution didn't just happen by itself. There were a bunch of other things that were needed. There was inventions, certainly. We need a lot of inventions. I'm going to show you some inventions. But we also need infrastructure and new business models. And new business models are an opportunity. There's lots and lots of opportunity in how we change manufacturing. I'm going to talk about inventions first. Invention is incredibly important to information technology. Invention after invention. There's lots of inventions in the manufacturing space. The one I've been working on is, for the last 4 years, is about low-cost labor and how we can't have that sort of Chinese low-cost labor in the US. People don't want those jobs. So how do we get around that and bring manufacturing more locally? So I've been working on a robot called Baxter. Baxter's a humanoid robot. It does look like science fiction robots, it turns out, in this case. And I'm just going to show you some video of how Baxter operates. Here's someone programming it. And she doesn't know about quaternions, it turns out, whereas current industrial robots, you have to know about quaternions to program it to do anything. She just picks it up, she moves the hand, she presses some buttons, the robot figures out what she means. Now it's going to do the task. Oh, and it says, oh, I don't like that kinematics that you gave me. So it moves the other arm out of the way, it optimizes the pathway, it figures it out, it's looking a little puzzled, so you get some feedback as this happens. Okay, now I know what to do. So the idea, and here you can, it's a bit washed out, but there's a graphical user interface. It's as easy to use as a smartphone. Here's the robot. Doesn't know what to do. She goes in, she shows it the objects it's supposed to see, it learns the objects, she shows the left arm and the right arm, different objects, tells them what to do with it, and in a matter of minutes, it's now able to sort these objects. But it's got inbuilt intelligence. So here, oh, it missed, damn. But it's okay, it figures it out, it goes and tries again. It's got error recovery built in, and goes off and picks up the object with its left hand that it's supposed to pick up and goes and puts it where it's supposed to be. And everything is force-based, so it feels a force, it lets go, and it's safe to be around. Oh dear, if that was a current industrial robot, she would be dead, but she's not. But you program this robot by grabbing it, moving it, showing it. You don't need any external language, you don't need an external computer, you just show it what you want to do, interact with the graphical user interface, you plug it into other machines, it interacts with the other machines, and it does real tasks in real factories. By the way, it's built in the United States. It's $22,000. It's a very low-cost robot built here. And the trick we play is we make it so that the end user doesn't have to know deep stuff. So the end user, sort of like an IKEA catalog, gets to build a hand for the particular task they want to do with a kit of parts. They put the pieces together. They don't need training on how to build hands. It's all very graphical. They build the hand, but now the robot can see the hand itself, so it's got to know what its own hand looks like. So we let the robot put it up against a red screen, see through its camera what the hand looks like, and figure the stuff out. We don't ask people to do complicated things. We let the robot do the complicated stuff. So these robots are now shipping. They're starting to be in factories. This is Mildred. Mildred has worked for 25 years in a plastics factory in Connecticut. This is 1 hour after she first saw an industrial robot, first time in her life. In that 1 hour, she had learned to program it. She had made it do tasks in the factory. She's getting older, as all our factory workers are getting older. But by giving them a tool that they can interact with and they can program, it's not like automation is coming from on high. They become the robot supervisors. They get control of what they're doing. And I think that's very important.
So, as you can see, that's a much different robot, much different style of programming. All right, so we've been producing these now and having these available since January 1st, and it's definitely had good market acceptance. And what we're finding is we're defining a new market space. And we're going to go over a few different things on Baxter that makes it unique from other robots. I mean, we're here in the heart of Silicon Valley. I mean, everybody's used to the high speed, type of robot, fully articulated, microns, repeatability, right? But you need safety cages. You need somebody who's technical to program it. That's not where this is targeted towards. This is targeted towards general manufacturing, right? Somebody doing things over and over repetitively, right? It will work with people, all right? We've taken this robot right off the, right out of the crate, set it up, and had people in our office from all different departments, accounting, come in, and within an hour, we've taught them how to use it. All right? My daughter, who plays with her Wii all the time, all right, actually learned how to use this thing without me even instructing her how to do it. So it's a whole different way of thinking about it. It's a different type of robot. All right? Very inexpensive. Rodney mentioned it's $22,000. That's for the base unit. Typically, it's around $34,500 with everything fully loaded. That includes a pedestal. Basically, what we have in the back over there. And as it says here, we're expanding the marketplace. We're not just looking at the places we typically would put a robot. In fact, that's not the places we really want to go. All right? We're looking at places that maybe a human's not the best thing in the world for, but it's going to work next to a human who supervises it. Next one. All right, easily integrated and instantly useful. All right, I've been dealing with robots now for 25 years of all different types, and typically we get a robot in, we have to bolt everything together, we have to integrate everything, there's a lot of cables, and it takes a couple hours, if not a day or two, to get the thing up and running. When we received our first robot, this was about 3 months ago. It came in a crate, actually 2 different crates. We had the torso, which is the main robot, and then the base. And within 1 hour, we had the thing put together. It's 2 pieces, plugs directly into the wall, 110, 6 amp. That's all you need. All right, we had it up and going, and we were programming it. Within the second hour, all right, we had it doing tasks. We've now deployed this at a number of different manufacturers. Names like Nike, Google, Toyota, all right, guys that make the little Connect blocks, all right, and it's the same thing. We're able to go in there within an hour, get it up and going and doing tasks. Rodney, when he went into this, he didn't go into it at the price point of a robot. They designed this so you could look at it as per hour. When you take it and you take the cost of the robot over the 3 years, all right, it's actually working for around $4 and $4.90 an hour. All right, doing simple repetitive tasks. Now here's the key thing. There are no safety cages required. A big part of our business at Balin is actually selling safety. All right, and typically around robots and work cells. And if you've ever been around some of these, some robots, and those things are moving pretty fast, and it will take your arm off, your head off, it will hurt you. All right, no safety cages are required for this. All right, the technology they're using on each of the limbs is called a series elastic actuator. All right, it's patented. It was developed at MIT. All right, and basically what it is, it's an actuator with a spring, and each joint has force feedback. All right, so if you want to, later during break go over and see Baxter, and we could have a movement, you can stick your arm in there, your head in there, he'll come up and he'll touch you, he'll stop, and then he'll try and recover again after you move out of the way. If you're in the way too long, he'll stop and he'll signal. All right, and you'll also notice on the face that we'll get to, he has different expressions. I'll let you know that, hey, get out of my way, buddy. All right? All right. It moves in a consistent, user-expected ways, right, building confidence. When you're back there looking at the robot, you'll notice, like, for instance, if I want to pick up this gavel, the first thing I do is I look at the gavel, then I pick it up. All right? Well, if you're with a standard robot, it doesn't have eyes, it doesn't look at that. You have no idea what it's going to do. So what the Baxter does, it looks at what it's going to do next. That gives cues, whether you know it or not, as a human, we pick up on it. All right? And the task is done as the person would do it. One of the things we do during the demonstrations is, if he's picking up something, I take it out of his hand. All right? You notice I'm calling it a hand, it's rubber. You start anthropomorphizing this thing after a while. And once you take it out, he recovers and he goes back and he tries it a couple of times more. All right? Until it errors out and gives you a cue that, hey, something's wrong here. All right? You teach it by demonstration. So there is no programming software on Baxter. All right? It is all based on the screen on there. You're teaching it what to do. You teach it to pick up a part, you teach it to set down a part. You can stack things, you can put things in arrays, all right, you can count. We can also connect to PLCs and other devices to get feedback and get cues. We can do sequencing and all those types of things. But there is no, at any time, sitting down and programming software. All right, I'm actually teaching it to do these things. Now, some people might say, especially in this valley, hey, I really want to program that thing. We do have a research version of this, which strips out the user interface, and then you can just go and program the robot operating system or ROS by Willow Garage. All right, so that is available. Also, I believe there's some colleges in here also. There is funding available through the government, grants, to purchase a research robot. All right, so if you have questions about that, let me know. All right, there's no programming language and there's no teach pendant. All right, I found this out the other day from a guy at Fanuc. The number one thing that gets broken, that gets replaced on their robots is a teach pendant. It usually either disappears or gets run over or something. All right, you see the yellow lights following them. Those are ultrasonic sensors up at the top. All right, they're not meant for safety, but they're meant to definitely let Baxter know you're around there, right? That you're in the area. And then, as I mentioned, if you're touching them, there's force feedback in every single joint, right? And when you're there, he'll look at you. If you touch his arm and you press a button, he's gonna look at you. If you interfere with things, he's gonna give you another expression. There's 16 different expressions that are on there, and they get a lot of research at MIT on what those expressions should be. There is an SDK coming out, hopefully by the end of the year, all right, that'll allow you to go in and write applets. All right, so just like you would on your cell phone, you have an app on top of that. We're going to be allowing people to write apps that will go on top of this. All right, the idea is Baxter is fully developed. His mechanics and electronics, everything is done. We're releasing software to increase the capabilities every 3 months. We currently include electric parallel grippers and also vacuum grippers, all right, that are usable on this. There are other people that are making grippers that will work on Baxter, and we will be testing those out as time goes on. As I said, we're developing and releasing more things quite frequently. Right now, we think there's probably over 100 people in Boston working on it. About 50 plus of those are all, very high level PhDs. And there's a lot of intelligence inside that building when you go back. You can also make custom end effectors. All right, we will help design those, that go onto the grippers and everything. And then we also have a pedestal that's on there that you can roll them around and you can take them from one spot and put them at another. We do a lot of lean manufacturing systems, so we work with Maddox in the past quite a bit. And we'll go in and we'll design work cells, all right? And what we found now, Baxter fits very well in that environment, and that I can take Baxter and wheel him up, train him in a couple of minutes, or if he's already been trained, start him on a task, and he works in that work cell that was designed for a human to augment a task that somebody else was doing. All right, as we said, it's fully integrated, so out of the box, it's ready to go. The only assembly is really putting the pedestal on top of the robot on top of the pedestal and plugging him in, booting him up, and he's ready to go. It's all self-contained, it's plug and play. When you put the grippers in, Rodney was showing that on there, how we put that on, how we adjust those. But there's a very simple thing. You go in and you say, all right, here's the gripper I have, here's the fingers I have, this is the distance I have. He's done. All right, and it makes it very simple for anybody to go in and do anything on it. And we have sensors built throughout the whole unit. There are right now 2 vision systems, one in each arm. All right, so if you go and look at it later, you have a vision system on each. All right, there's a vision system in the head. All right, there's one in the chest, which might be going away. We haven't quite figured out if we're going to keep using that yet. All right, there's also a distance measurement sensor in each of the hands, or each of the arms there. All right, so it can tell the distance to the surface, the work surface. That's pretty much it on the basics of Baxter. Like I said, very new to the market. We just released version 1.1 of the software, which has a lot more capability than version 1.0. And we're releasing a new version pretty much every 3 months. In the back, we do have information on them. We do a series of things called Meet Baxters, right? Where it's at our facility, or depending on the size of your facility, we might bring them out. If you have interest in doing that, it's a great way of seeing what he can do. All right, it's about 20 minutes of PowerPoint and overviews, and the rest is all hands-on. All right, so feel free during the break, come back and see him. Also, at the end of the day, for some reason, people love taking pictures with it. Feel free to take pictures with it. We'll move the table, and you can get a good picture and give it to your kids.